So today we're going to be talking about functions and control flow, which are basically two things that we haven't really needed to use in R yet, but as you go farther in your R careers, as you keep coding, as you are doing more complicated things, these really come in handy. So we'll first cover control flow, and then we'll get into functions. I'll go over what those are and what they look like. And I'm going to put an asterisk at what I said earlier. We've been using functions this whole time. We just haven't been building them ourselves. So it should be familiar, the format, but we're going to be building them ourselves. So let me share my screen. You should be able to see class 20 here, and we'll get started. So as I said, first we're going to talk about control flow, and then in a while we're going to talk about functions. So we have seen a tiny preview to control flow when we talked about case when, where case when was if a certain condition is met, then do this. If another condition is met, then do this, etc. So control flow is basically how we control which actions are done when based on conditions. So this is generally done with if-else statements. Case when is a generalized version of if-else statements that is most useful in the case of like a mutate, whereas if-else can be useful in other instances because it's more flexible. So let me show you what this would look like. Right. If condition is true, then we have curly braces and we say, perform this. So if something's true, we do the thing in curly braces. Otherwise, we can leave it here and just say, if this is true, do this. We could also say if else. So if this is true, do this. Else. So now we're looking at a different condition or everything else that doesn't match the condition. Else do this other thing. So we're saying, let me put some bold on these. Oh. So if a condition is true, do this. If otherwise, basically, is what the else stands for, do this other thing. So here's a quick example. So if we have a value of x is 8, let's run that. We can then say if x is greater than or equal to 10, then let's print to the console. So this just means print something out, generally text. Print x is greater than or equal to 10. So our condition here is if x is greater than or equal to 10, print x is greater than or equal to 10. And a trick here, every time you're writing control flow or functions, when you want to run it, you can do the entire cell. Or if you want to run it and you try to just click the part that's inside the curly brackets, it's not going to do what you want it to do. So you always have to click on the part before the curly bracket. I constantly mess that up, so I'm saying it now. And nothing printed out here. So I just ran it. I ran this function. I ran all 3 lines and nothing printed out. Does anybody have an idea of why not?
Because x is not greater than or equal to 10.
Thank you, Semyon. I have a feeling you're going to be very helpful in this class today because you're pretty good at functions from other programming languages, I'm sure. So x is not greater than 10. And so I didn't give it an action to do because x is less than 10. There's no other action. So I could build onto this and I could say, if x is greater than 10, do this. Else, which means otherwise, do this other thing. Else print x is less than 10. Now I have to move my cursor up here and run it. And now we can see I've ran this entire control flow statement and it printed out x is less than 10. So in literally here, let me get out my annotation so I can draw it. We've got x. And then there's the first thing that's going to be evaluated is x is greater than or equal to 10. and this can true or false. If it's true, it's going to print out this thing. If it's false, then it's going to, because there's no other condition, any false one is then going to print out x is less than 10. So hopefully you can kind of follow this. X is greater than 10. If it's true, it would do this. If it's false, it will do this. Now let me, yeah, I'll just redraw in a second. No, I don't want to annotate. Stop. There we go. But, you know, this is a very specific example. This might not be super useful in your everyday practice, doing greater than or less than, but in control flow statements, especially in functions, this will be useful. Let's build in now a else if statement. So I'm going to add it up here to our little dummy function, I guess you could call it, where in the middle, before we do else, I'm going to have an else if. So the order here is if this, then if this other condition. So we're adding another condition, and then we have a catch-all else. And then I'll draw this out in a second once I've added it here. So if I want to add an else if, it always goes after the if and before the else, because else catches everything else. I can add an else if here, and then I can add an else at the bottom. You'll notice I keep doing curly brackets where I have something in the middle of the line. That's just, well, in the middle of the line is not very descriptive. I end the line with a curly bracket. I have something in between with a tab or two spaces, and then I have another curly bracket to close that, and then I continue on the statement in the same line. This is general style formatting practice for these control flow statements and for functions. Hopefully that just helps you read it better, because everything that's indented is the thing that's happening in between. So now let me actually fill out my else if. So if I want else if to be, and here I actually need another condition. So sorry about that. A different condition. See if I can get more of this on the screen. There we go. Else if x is greater than 5. So now if x is greater than 10, it's going to print this. If x is greater than 5, we're going to say if x is less than 10, but greater than 5. And then else print x is less than 5. So because x is 8, let me draw this before I run it. Annotate, draw, there we go. We've got x, and the first thing that's going to be evaluated is if x is greater than or equal to 10. If this is true, it will print out this first condition. If it's false, it's going to be evaluated on another condition, which is x is greater than 5. So you can see here, x is kind of being bounded between 10 and 5 because we've already done the 10 condition. If x is greater than 5, I'm sorry about the beautiful drawing here, but I'm sure you all get it. If x is greater than 5, it'll be true and it'll print this statement. And if it's false, it'll do everything else, which is x is less than 5. Hopefully that helps us understand how these work a little bit better. We could have a lot of else if statements, and the order really matters here. So let me run this. X is still 10. So when I run this, it says x is less than 10, but greater than 5. One thing we do have to note, though, is that if I change x to be something else, like a word, this could break my if statement. And so later on in this class, we're going to learn how to be defensive programmers. But now it says x is greater than or equal to 10, even though I used word as the input. So as I said, we just have to be careful on what we're inputting into our control flow. Okay, now finally, whatever x evaluates to is the thing that's going to control the two true false. So if I have something like x is assigned 4 equals 3. 4 equals 3 is going to be evaluated as a true false because I have the double equals. If I do this in the console, you'll see that 4 equals 3 is false. 4 does not equal 3. They're different numbers. Now, if I put that into control flow, where I could say something like if x, and just have x, if x, so if true, if false, because it's going to be read as if true or false, I can say 4 equals 3, because that would be if true. Otherwise, else, 4 does not equal 3. Now I can run this. So now x is equal to false. Then I can put it through here. And because the condition is literally just looking for it to evaluate as a true false, and it's already a true or false, I'm going to get 4 does not equal 3 as the output, which is good because it does not. And there's no error because the condition, as I said, is already been evaluated. We're already getting a true false. So does anybody have any questions about this kind of if-else funny business before we continue on? The code is very straightforward. That doesn't mean that when we're building them ourselves, we're not going to get lost. But it doesn't look like anybody has questions. So the important thing is, let me fix where my bolding is here. So we've got if, do this, else if, and we could have a lot of else ifs, and then else, which is the catch-all for everything else. Great. So now we're going to get into actual functions. Now, the first thing that we need to know about function making is this. It's a software engineering principle called DRY. DRY stands for don't repeat yourself. So what this means is when we're writing code, if we have to copy and paste chunks of code more than once, we should probably write a function instead of copying and pasting code and changing certain things. So you've probably experienced this, especially before we learned like mutate across, where you wanted to take the mean of multiple different variables and you were copying and pasting lines of code of, I don't know, let's say population equals mean of population, comma, NA remove equals false or true, parentheses, and then copying and pasting that and changing out population for another variable like life expectancy. Well, the more you do that, the more likely you are to introduce errors into your code because each time you copy and paste it, you might forget to change something. But also, it's extremely repetitive and harder to find errors in because you're just having the same code repeated so many different times, and you have to like take basically a pen and read through every single line to find your error. That's not what we want to do. We want to prevent repeating ourselves so that we're able to make our code more, a lot of things, more reproducible, more debuggable, and the copy paste update lifecycle is like not very efficient, let's say. So if you're working on something where you're finding yourself copying and pasting a chunk of code and then changing part of it more than once, you probably want to write a function. So that's what we're going to learn to do today, is how do we write our own function. So a function basically has a name of function that gets assigned to, and then this is literal, function of parameters, curly bracket, and then what to do with function. This is a very basic outline. Now I'm going to go into depth of what that actually looks like and start building a function with you so we can all follow along. So we have a name that we want the function to be called on, a defined set of inputs and outputs. Don't worry, I'll go over this again. And then what we're going to do with the function. So I could have a very basic function that has no inputs and outputs called hi. where my function is I always have to write function to declare that this is going to be a function. And in this function, I have no inputs and outputs. It's always going to do the same thing, and it's not going to change depending on what I'm doing. After that, I'm going to put my curly brackets. I always code like this with the curly brackets, even if my function itself is very short. There's other ways you could do this without curly brackets on just one line, but I find this easier to read, so I'm going to always do it like this. And I can say cat, hello. If you remember from our strings week, cat is just a way to evaluate whatever's here and print it out into the console. I like to use it over print. They both work though. So if I run cat hello, nothing happens in my console besides just saving this new function. And so let's say if I ran my chunk, there would be no output to the chunk. But in my coding environment up here, you can now see I have data, because I loaded the Baltimore data earlier. I have values, x equals false from earlier. And then now I have a new thing that we've probably never seen before called a function. I have a function called hi. It's a function with no parameters here. I can always, I believe, click this to view what the function does and view its source code. So again, I ran this, it evaluated, it's now saved as a function, but I haven't actually run it. So I can run it now in the console with hi parentheses. Every function in R has parentheses after it. That's how you know it's a function, whether or not you're using options from it. So if I run hi parentheses, now my console will now print out hello. It's kind of cute. I like it. But what if I wanted to now introduce my name? I want it to say hi someone. I can now start to put an input parameter. So I'm going to just copy and paste this just so I'm not editing the first one in case you guys are following along precisely. So to introduce a parameter to this function, I can put here name. Name will be a special option that I can call on from inside the function to do something special with it. So this is like when we use the main function when we add name na.rm equals true or false. This is an option that we're adding. So I've got the function, I've got name, and then now I want to do cat hello, and then I want to do cat name. That's all I'm going to do to change the function. I'm going to add an option called name. And let me put my hi up here so we saw what it was. So now, after I've run this, and remember, because it's a function, we've got the curly brackets, you have to click before the curly bracket in order to run that section. So I always do Control Enter. Now I've run the section. So now I can say hi name equals, let's do Delilah. So now when I run it, it says, hello, Delilah. This is not beautiful because there's like an exclamation point. There's no spaces. I could edit it. I could make a line break here. We've learned all of these things. So now it says, hello, Delilah. This is a parameter now that we've input. Anytime I change this, you can see it doesn't say Delilah anywhere here. This is a parameter. I can also say, hello, Kelsey. And now it'll print Kelsey because it's always looking for that parameter to input it. Now let's make this function a little bit more fancy. I don't like that it's on 2 lines. What if I wanted it to have just 1 line and I wanted to, let's say, glue them together? So I'm going to copy and paste the function, put it down here. And now instead of saying cat hello, cat name, I'm just going to say glue. You could also use paste here, but I'm using glue. You could say glue hello name. So if you remember the glue syntax, glue takes any variable or parameter inside of curly brackets, any object, and it will basically put that with the greeting. So we've got glue hello name. So I'm going to run it again. That updates my function up here. Now let me paste these ones down here to see what will happen. So we've got hello Delilah, nicely pasted together in a nice format. So if you've coded in other languages before, you might wonder why we're not doing a return statement here. A return statement, which we're going to build right now, is a way for you to explicitly say what you want the function output to be. So I could say here, greeting, and I could save greeting as an object, and then I could say return greeting. This is better programming practice, and this is what I'm going to do from now on in this lesson, and I suggest that you do, but do know that anything that's going to print out, so before, because I wasn't assigning this, that was automatically would have been printed in the console, R will automatically use that as the return. So you don't have to use explicit returns, but it is better practice to be explicit and say, I want this line to be outputted. So let me run that again, but you'll see it's the exact same output. We just have greeting being saved and returned. But I also want to point out that greeting, even though it's saved here, is not saved up here. It doesn't become an object that's saved outside of the function itself. Okay.
I have one question.
Yes, Raphael.
If you do hi and then just put in apostrophes Kelsey, for example, it's gonna do the same thing without calling
yes.
name.
Good point, Raphael. So you don't have to be explicit about name because there's only one argument we've included. So you're easily able to say hi Kelsey, and then it'll print out hello Kelsey. Now let's make it a little bit more complicated, because now we can add in, and this is our final example for our hello, we can add in multiple parameters. So if I want to take this function and I want it to take the greeting itself, so I want to be able to change hello, hi, howdy, whatever I want to say, and take the name, and then let's say I want to take who the greeting's coming from. So I want to take 3 parameters. I want to take the greeting, the name, and from. So here, instead of hello, I want to say greeting blank, exclamation point, and then I'm going to kind of make it like a quote. So use the dash to indicate this is from, and then I can say from. And I can still say return greeting because I'm just editing what is being pasted together. The functions here now, again, I can look at the source function by clicking on this little scroll, I guess you would call that. Now let me throw in another version of the hi calling on the function. So I want to say hi, maybe instead of hello Delilah, I want to say hey there Delilah, because, you know, top song of the 2000s. So hey there. So this would be my first argument, which is the greeting. So I want to say, hey there, and then name equals Delilah. And then let's say this is from the Plain White Tees, which is the band who sang the song, Hey There, Delilah, What's It Like in New York City? So if I run that now, I'm going to get a nice output. Hey there, Delilah, from the Plain White Tees. This, again, is a small dummy example of how functions work. Generally, you're not just going to be pasting things from the function syntax, but you might be. And so this is really good to go over. I can easily change this to any other sort of what's up, Kelsey, from mom, whatever I want to do. I can take this generalizable syntax and build off of it for other uses. So speaking of that, let's now switch from our hello example to a more mathematical example where we will be converting temperatures between Fahrenheit, Celsius, and Kelvin. Super fun. So let me make a new one and call this.
Just one quick question.
Yes.
The greeting you put in the curly brackets in green is not going to be the same as the one that's on orange, right?
Correct. So that's good to know, Raphael. This probably isn't the best programming practice because I called greeting both things. Maybe I should call this salutation. Call it something else so I could be explicit about what's being called where. Because if I wasn't careful, I might get this parameter printed out on accident. So it is good to be explicit. You're right. So I could rerun that. It's going to be the same output, but now I've been a little bit more explicit. I could also just say X, for instance, but
Okay.
yeah, naming variables is important to pay attention to. So now we can talk about temperatures. First, I will do a function that converts Fahrenheit, and this is a hard word to spell, so Fahrenheit to Kelvin. I don't know that much about temperatures in terms of like Kelvin. I've never used Kelvin, but we can build a function that will convert Fahrenheit to Kelvin. So I want to name my function Fahrenheit like that to Kelvin. So I can really remember I need Fahrenheit as an input to get Kelvin as an output. So my first thing I always have to write when writing a function is function. And I have to say what I want as my input parameter, which it could be multiple, but in this case, I want my temperature in Fahrenheit. And I'm putting temp underscore F to remember that I have to put it in Fahrenheit. That's the point of this function. And now we can put our inside of the function here. So now I want to create temperature in Kelvin. So to convert between Fahrenheit and Kelvin, it's kind of funky, but we're going to take the temperature in Fahrenheit minus 32. So that'll bring us down to 0. Well, if it was 32. And then multiply that by 5 divided by 9. And then all of this goes into a parentheses. And then add 273.15 to that. I didn't design this. I don't understand. I know part of this is converting from temperature Fahrenheit to Celsius, but the other part, who knows? And then from here, I want to return temp K. So I want to return the temperature in Kelvin. This looks very similar to the other function we just wrote because there's only one line of manipulation here. It's just using numbers instead of text. So I can run this now. You'll see Fahrenheit to Kelvin gets added to my functions list. And if I want to run Fahrenheit to Kelvin, I can now say, what's 32 Fahrenheit in Kelvin? And that's apparently 273.15, which makes sense based on this math. So let me go over the different parts here that we have. So first, we have kind of our ingredients of what goes into the function. We define what we want to do with those ingredients and what we want as an output. I can also run like 212 degrees Fahrenheit, which apparently is 373 degrees Kelvin. Okay. So now let's write another function that will convert Kelvin to Celsius. So let's convert Kelvin to Celsius. And to convert from Kelvin to Celsius, let me write this here, we subtract 273.15. So let's write this one as a group. So you all have to speak up, which I'm sure is your favorite. I'm going to name the function first, so you don't have to. We'll call it Kelvin to Celsius. Save that as an object. Now, what is the first thing I need to do when making a new function?
Put the function command.
Thanks, Sydney. So we have function with parentheses. What goes inside of these parentheses? Or what are we going to put in the parentheses?
Temp K.
Great job, Raphael. So temp K, and I'm sure Raphael is saying that because we're taking Kelvin and we want to change it to Celsius. So how, based on this hint, can I change Kelvin to Celsius?
Would you do temp K minus 273.15?
Temp K minus, yep, 273.15. I'll just paste that in. So I
assign that to temp C first, though.
Good, Mary, good. And then because we like to be explicit, we can do a return here where we want to return temp C. I literally could have left it with just temp K minus 273, but I really like being able to see temp C. That reminds me when I'm looking back over this code in a year from now, that's what's being outputted. So now I can run this, and now I can see to get from Kelvin to Celsius. Let me scroll up because I think 273.15 Kelvin should be 0 degrees Celsius because I know 32 degrees Fahrenheit is 0 Celsius. So let's try this. Kelvin to Celsius, 273.15 should be 0. Good, which makes sense because of the code that's here. Man, I wish I knew more about Kelvin. We can do Kelvin to Celsius, 300. That's 26 degrees Celsius. Pretty warm day, but not too hot. It's probably a nice temperature. So this is great. We've got Fahrenheit, we've got Celsius. Where functions really come in handy is when we're combining functions together. So I could actually build both of these functions together to build a Fahrenheit, that's not how I spell it, Fahrenheit, that looks right, to Celsius function. So now if I want to convert Fahrenheit to Celsius, a lot of people here, because of how we've been programming in this class, your first instinct might be, well, after I do library tidyverse, to do something like first Fahrenheit to Kelvin, let's say 32, and then pipe that into Kelvin to Celsius. That will work. We can pipe these two functions together. But what's really better is to build a function. So this is placing two functions together in our script, but we could build a function together that converts Fahrenheit to Celsius. So I could say Fahrenheit to Celsius, I'm just going to say Celsius, and that would be a function that takes the input of temperature in Fahrenheit. Do my curly brackets. And now what I could do is I could say, I want to take my Fahrenheit to Kelvin first. And then next after that, I'm kind of doing dummy code first before I build everything out. So after I take Fahrenheit to Kelvin, then I want to take Kelvin to Celsius. And then I'll do a return. So I can take Fahrenheit to Kelvin. So I can take temp F. And that would give me temp K, because we start with Fahrenheit and then go to Kelvin. And then I can take temp K and print out temp C, and then print out temp C as the output. And you can see here, because we've got so many different temps, it's really useful to have that nice naming where we've got temp underscore what type of temperature it is, so that we can follow this easily. We've got temp F to K, K to C, and then print C. So now I've got three functions. I've got Fahrenheit to Celsius, Fahrenheit to Kelvin, and then Kelvin to Celsius. I've got the entire triangle of how to convert between these three, building on the other functions that I've already built. It's pretty nice. So if I put Fahrenheit to Celsius now, as we could see, I could do like, I don't know, 45 Fahrenheit, that'll print out to 7 Celsius. That's not a nice day. We've got Fahrenheit to Celsius. Here where I live, I think it's about 92 today. It's kind of hot. 33 degrees Celsius. That's toasty. But what if I did Fahrenheit to Celsius and put hot? It gives me an error, which is good. It does give me an error, but this error is not super useful. Non-numeric argument to binary operator. I think most people in this class, when they first see that, they would just Google it and find on Stack Overflow what this means. What we can do, though, because we're programmers now, is build in error statements that can be printed out that are actually helpful. So this is where we're going to get into defensive programming. So I'm gonna bring back my first Fahrenheit to Kelvin function. So I'm gonna copy and paste this inside a chunk. And now we're gonna start working on how to make this like defensive. How we're going to defend against wrong inputs so that this is both useful for the person who's using it, which is often ourselves, and we want to be nice to ourselves, but also make it more robust so that it's not giving an answer when it shouldn't. So to create an error message, I'm actually going to use control flow, which we were learning earlier, like if-else statements. So the first thing that I want to happen when this function begins is to see, is temperature numeric? Like that's the one thing I really care about here. Is this a numeric value? So I'm going to do an if statement, and we have if parentheses, and then we have brackets. I always have to remember that. The first part is parentheses. We're going to say if is not numeric. So is numeric, and we put the exclamation point in front to say is not numeric. And we'll take temp f. So if temperature f is not numeric, do this thing. And what we're going to do is we're going to do a stop. So a stop is literally a different control flow statement that says stop the rest of the code. Whether we're in a if statement, no matter where we are, stop the entire thing. So break, basically. We're going to say stop, and here we can actually put a lot of different things, which is nice, but we can customize our error statement. So I could say here, temp f must be numeric. And then if that if statement is not triggered, so if it is numeric, that will just be ignored and the function will continue on as normal. You could also do else, but you don't have to. The if statement is just saying, if this thing, do this. And then if it doesn't get triggered, it'll just continue on with the rest of the function. And because it's inside of a function, you don't technically have to do the else. So let me run this. And then let me try to do Fahrenheit to Kelvin, because that's one we just customized. And I'm going to say hot again. And now we have an error code, temp must be numeric. That's nice. Obviously, I should have this lowercase because that would be more useful. So we know exactly what it's talking about, but temp f must be numeric. Wonderful. Now, if I want Fahrenheit to Kelvin 54, it'll give me normal output. Nothing there has changed. We've just added in sort of a layer of security to our function. I can also build on the function in a more fancy way. So I could say temp must be numeric. Let's do a line break. Temp must be numeric. You have supplied an object of class. And then we can actually call on the class of the object that they supplied to tell them, you think you're giving me numeric, but you're actually giving me, and then we do class of temp. So stop can evaluate things for us, tell us what the class is that they've given us, and print that out. So you have supplied an object of class character. That's pretty nice. If I was an R programmer, well, if I am an R programmer, but when I do things and I get errors, I would much rather see an error statement like this to tell me what in the world went wrong, because oftentimes, as you all are very aware of, the error statements are not that helpful and it's hard to figure out what went wrong and where. Building nice stop statements in our functions is wonderful. So at this point, we've built a function, and this is literally what all of the things, like when we run mean, I don't want the parentheses, when we run mean, it is a function, and it uses the method mean, and it's this fancy environment thing. We don't need to worry about that, but all of the things that we run are functions that are built like this. So this is the basic programming block for R and for all programming languages in reality. But now we know how to write a function, which is great.
I have a question.
Yes.
What if you happen to like overwrite the name of a base function? What would happen? Would it even let you?
I think it's not going to let you. So let's try. Let's say instead of Fahrenheit to Kelvin, let's try mean. I know for a fact that if I restart R, it'll fix it. So if I do this on accident, it should be okay. Yep, I just overwrote the mean. So now mean is this other thing. You kind of have to be careful with it. But if you notice when I wrote mean here, it automatically printed out that there's this thing in the global environment called mean. There's these other things. It kind of is telling you, hey, this already exists, so don't write that one. But it's not giving me an explicit error. So you do have to be careful. Most things you're going to write are, they're for you. And so they're specific. But if you know, when we load the tidyverse, for instance, let's see if I can scroll up to where we did. No, lower. Okay, well, we loaded the tidyverse at some point. Okay, well, I can't find it. When we load the tidyverse and when we load other packages, you'll often see that something is masked by something else. So that means that filter, for instance, stats, which is a base R package that comes preloaded in R, is always on, has a function called filter. But we know that dplyr also has a function called filter. And so this is the exact same name, and whatever one's loaded last will be the one that takes preference. You can choose which package it comes from by saying something like base. I don't know if you can do base like that, but you could say, I want for sure to use the dplyr filter command. So that's how you can say which filter you want. But yeah, it can be dangerous when you're overriding each other. But now if I, for instance, say session, restart R, hopefully that one goes away. I'm sure it will. I just use this little broom, which I don't think I've mentioned in quite a while in this class. That just clears all your rear objects from the workspace. So right now we're close to the end of class, which is great. That means we're probably going to end a little bit early, but I want to mention two other things. One thing is how to source your functions. So if I have these three functions that I've just written, oftentimes I don't want to keep them in my R Markdown where I'm actually actively working because I might want to use them in the future. So if that's the case, I can create a new R script. At the top of my R script, we should always write who wrote this and what it's for. So I can say written by Kelsey Gonzalez on 2021, 0405. Purpose to convert temperatures.
Okay, sorry, what kind of new document did you just open?
So I did an R script. So I
Okay.
picked new file, R script. So instead of an R Markdown, which we almost always work with, I did an R script, which any text we write now, we have to comment out, but that's because the entire R script will get run when we source it. So let me show you what I mean with that. And I'm going to paste in my functions. So I have my Fahrenheit to Kelvin. Let me find my Fahrenheit to Celsius. I'm going to put that last because it relies on the other two functions. And then I've got my Kelvin to Celsius. I feel like I need to make this bigger. So I've got my three functions here now. And I'm going to save this. So I'm going to save this in my project folder, but I could also save it somewhere closer to the root of my computer. Oh, that's the folder I wanted. And I'm going to call this temperature conversion. You'll notice the text is really small in here. It's because I'm using a small screen. Temperature conversion.r. Save. So now in my folder, I have a file called temperature conversion.r. I'm going to go ahead and paste this entire thing into the chat just in case you didn't get some of these functions working. And now when I'm working in my R Markdown, I can basically call on those functions into my R Markdown. So I can say, hey, go grab these functions from this other file so I can use them and work on them in this file that I'm working on. You could see this being useful like in your final projects where maybe you build a function, but you don't necessarily want to have it live in your R Markdown. You want to call on it from somewhere else. So I can here say source, which makes sense because I was talking about source functions. And basically source means I'm going to call on that other file. So because it's in my same directory, I can now say file equals, and then I want one called temperature conversion. Let's see if it'll autofill for me. It doesn't look like it. Maybe if I do parentheses. There we go. Okay. If I do my quotation marks, it'll autofill my temperature conversions.r. And recently I cleaned my directory, so there's no functions here. And when I click run, I will now load these functions from this other file. And as I said, this can be really useful. Some people use this sort of programming practice to run all of their data cleaning. So when you first load in your data set and you want to mutate and you want to summarize and you want to add all these things to your base package and then join in all these other things, some people, they make it in an R script like this, and then they source it so that they don't have so much code kind of bogging down their R Markdown document. So some people use the same kind of practice. This temperature underscore conversion R will run the entire R script though, which can be good or bad. If you have things in there that you don't want run, you're gonna need to comment them out with like the hashtags. But it also is a good thing because I can say, I can add in a message. So I can say message, which will print out to my console, loading functions from temperature conversion.r. So now if I save this and I get rid of my functions here, now when I run my source, it'll actually give me a message letting me know, hey, I'm loading functions, give me a second, and then it's ready. And it's now loaded these functions. That's pretty nice, especially if you're not sure if you ran something. You want to make sure that it actually loaded. And you could do this, you could do a message in front of each of these functions to know that they properly loaded, for instance. So that's most of what I have for sourcing functions, for writing functions, writing defensive functions. There's more to this kind of topic that we're going to be talking about next week, specifically how to do loops and next and all of these other kind of more second level things, but this is a really great introduction. Most of the time though, when you're writing these functions, things are going to break, and that's very normal. And I don't want you to get frustrated when they break. You just need to know you've written your function. You need to know what's going on where. So one great thing you can do is as you're writing your function, you can have it print different things. So if I had, 5 different steps to this and I wanted to make sure temp K looks like what I want it to look, you can always temporarily write in like cat temp K and then continue on with other parts of code so that as the function's working, it's printing out so you can see what happens at each stage. That's one really great thing that you can do. Another thing you should do is every part of your function, you want to be documenting it a little bit better than I have here. So I'm going to take a few minutes and let's explore what exactly we're doing in each part and comment it. So for instance, the first part, I'm going to write a comment and say, make sure temp is numeric. So that when I'm looking at this, I can see, okay, that's what that part's doing. I don't really need to read the code. I can read the comment to know that this is a section. And then here I'm going to convert temp to Kelvin. So here it would be useful if I wrote temp F. Temp F, and then here temp F to Kelvin. And then now I could write return temp, but it's very obvious it's literally just return temp. So maybe I don't need to write code there to tell me what it's doing. But when these get longer, it's really important to kind of put these flags to let yourself know what's going on where as you debug. So the general practice here when we're testing our code is to write the function. After we've written the function, to comment on the parts to document what's going on where. Again, that helps you in the future, that helps you to debug, that helps you to, when you decide to change the function and make it more efficient, all of these things that will help you for. You can then make it a source file so that you can load it in as a separate file. Then you experiment with it, make sure it works right by running things like hot, or let's see, something like Fahrenheit to Kelvin true, which is a different type. So this is a logical type, true or false. Will this run? No, because I built in a good check that says it has to be numeric. What if I put in Fahrenheit to Kelvin and I put a vector of numbers? So if I put 45, 97, 96, will that work? Yeah, it gave me 2 different Kelvin outputs. That's good. That's the good behavior that we want it to do. It's able to run Fahrenheit Kelvin on both of those numbers, but it's good to test that as well. So that would be the next step, would be testing it, making sure it works as you want. And then you keep working on it until you find more bugs. One thing I forgot to mention earlier, which I wanted to make sure I did, but I forgot, was when we first built this error message here, some people probably got a pop-up that brought them up to another screen. If you did, which it sounds like maybe no one did, which would be great, under debug on your top menu here, there's an on error button. Hopefully everyone says message only, but there's also fancy built-in debugging tools in RStudio to figure out where your error was and why. In our case, we built in a stop message so that when it broke, it would tell us why. We don't need to go into the debugging section. So mine originally was break in code. I changed it to message error for this. Our library calls basically calling on cloud-based source files with all these functions, the same way we did our temp conversions. Kind of, Mal. That's a good question. So right now, our functions live in a R script that get called with source. When we call library tidyverse, let's say, that is not a R script, it's a package, but that's like a more complicated project of R scripts that can kind of talk to each other. And they're not living in the cloud, they're actually living on your computer. Somewhere near the R library. I never remember where they're at, but if you click packages, I think you can see their base address when you click it. But it's going to take a second because I have a lot of packages. Browse packages on CRAN. Maybe if I click this. Okay, no, I don't. It's on my computer. It's not in the cloud, and that's why when you install packages, it's downloading them into a certain path towards the base of your computer where all of your R packages live. When you say library lubridate, it will load that package, which it can find from your base computer, because there's a folder called lubridate, which is kind of like an R project, which is crazy. I believe I can get it to be, no, okay. I thought I might be able to get it to print out my address of where it's coming from, but that's okay. So as I mentioned earlier, we can see what objects are being masked. So lubridate is masking date, intersect, set diff, union. That means we're going to have issues between those packages if we're trying to use both of the functions or we're trying to use the wrong function. Very common with dplyr. You may have already run into that. Yeah, so in the future, if you get really into this, I mean, I find these fun to do. Next week, we're going to work on actually some problems from HackerRank, which is a computer programming algorithm building site, kind of, where they give you challenges and you have to try to answer the question in code. For instance, we did that, what was it called? Fizz buzz question a few weeks ago, where we had to say if it was a multiple of 3, it was fizz. If it was a multiple of 5, it was buzz. Those kind of questions. We're actually going to go over 1 or 2 of those next week because some people find this really fun. And if you find this really fun, you can start building packages for things that you think need built. It's not that difficult to build a package, which is crazy. And you can use things like, there's these 3 packages, Roxygen or R-Oxygen. I said both. Use this and test that. Those are all to build in tests for your functions to make sure they're working right, to set up packages nicely. There's a bunch of things built in for if you decide you want to get more into building functions and scripts, they're here for you, which is really cool. And you can build a package just for yourself, which is awesome. It doesn't need to go to the entire R community. So that's what I have for today. I'm going to stop my recording. Let's see, stop recording.